All right, physics reaction video number 67. I think I did physics lecture notes or something like that. This is from just a few days ago, I believe.
Bless you in the comments, I just sneezed. Okay, what we're looking at here are some notes regarding entropy. And really, we're talking about the second law of thermodynamics. Now, even though this is the second law, it's really the third law, because there's that 0 with 1 in front. But this is our second law of thermodynamics, and it deals entirely with entropy, often thought as like the chaos or the disorder of a system.
Cool.
Something that we know is that energy or heat must flow from it goes from hot to cold. You cannot let the cold out of your house. So like in the summer, if you got the AC on and you open up a window and your parents are like, shut that window, we're not trying to cool the outdoors. You cannot cool the outdoors. It's not a thing. The outdoors is going to heat your house. Or in the winter.
You know, it's so interesting. I love that. I say that kind of stuff all the time. Oh, well, cold is not a thing. Heat has to travel. And yet I've been really reflecting on it almost all the time. People are talking about air masses, right? Letting the warm air in or letting the cold air out. And when that happens, it's fascinating, right? You're literally shaking a chunk of your house out, the air molecules that were in there, and they happen to be colder. So I totally get what he's saying, but I think that it's a hard sell for some students. Just a couple of comments on what's happening here. First of all, that 0th law. There's a really, really great optical illusion where you have this pillar casting a shadow on a tiled floor. And it says, you know, hey, do you believe me that this tile here is the same color as this tile over there? And it's basically, how could that possibly be? And I use that to get students to understand the 0th law. I'm like, I know it sounds weird. You put these two things in contact, they reach the same temperature. Just trust me. But I love the fact that it sounds like he spent some time on that. That's super cool. So the second law, this thermo stuff, I think I always am passionate to learn more about how to teach this, because I think it's super, super tricky, but it dominates so much of our lives. And to really take some time to get it right, I think it is super smart. I think my favorite approach is from the 6 Ideas series. That's when I was reading through that, preparing some lecture notes, I thought, oh, okay, I like this the most. But it really sort of pointed out to me that there's just so many different ways to do this. This idea that heat flows from hot to cold is so fascinating, right? Because it's not conservation of energy. And so there's nothing wrong with heat flowing from a cold thing to a hot thing. From a conservation of energy perspective, as long as you don't lose anything, you're totally fine. So this is the new thing. And, you know, there's people who talk about how this is connected to the direction of time, right? That entropy helps you understand when a movie is playing backwards, but conservation of energy doesn't. Neither does conservation of momentum, but entropy does. So I'm really, really excited about this.
If you're heating the house, you can heat the outdoors, because we have to have fast-moving particles interact or collide with slower-moving particles to transfer that heat energy. It is always the high average kinetic energy, the higher temperatures, striking the cold, the lower average.
So it wasn't clear to me before, but the way he's looking around tells me that this is a live audience, but also being captured for the people who aren't there. Just kind of the way he's looking around. So I'm really curious to see how well he deals with this sort of hybrid audience. We'll look to see if that is an issue. The other thing I was going to point out, I'm super, super jealous. I love this version of OneNote. I'm using a different Windows machine at work now, and it required me to upload to the newest OneNote, and the newest OneNote stinks compared to this one. I love this one. All my tools, all my stuff over here. So I'm frustrated about that, and I'm jealous.
Kinetic energies with the average temperatures. And that's how we transfer that energy. So we are always transferring energy from hot to cold. Now, this is if things are left to their own devices. This is the natural order of the systems. Yes, we can cool things down. I know refrigerators are a thing, but in order for a refrigerator to work, you have to provide power to it. You have to have compressors and all sorts of systems and chilling factors to get that to happen. You cannot just have a box and tell the box, get cold. That's not a thing.
Awesome.
Okay?
Love
So heat flows from...
And for me, refrigerators are so interesting because what I talk to my students about is the only way you could possibly suck some heat out of that can of pop that you just put in there is to expose it to something even colder. So that's what refrigerators do. It has to sort of expose it to something even colder. So the Freon or whatever is in your pipes of your refrigerator is work is done to it, as he's talking about here, to get it even colder than that can of pop or whatever you're trying to refrigerate, so that then the heat inside that can is like, oh, okay, yeah, I'll go over here, sweet. And so it really helps to understand just how hard it is to do these things. And I love that analogy of what he said, that you can't tell a box to be cold.
That's not a thing. Okay? So heat flows from hots to colds until that temperature is normalized throughout them. Now, because of this natural process, it shifts things from order to disorder. And this is where that idea of like chaos comes. And what we mean by this is, think about a block of ice. A block of ice has a nice lattice structure. It's a solid. It's well organized. As I continue to give energy to it and I heat that ice up, eventually it will go through a phase change. It will melt. When it melts, it loses that nice solid structure. It becomes a liquid. The particles are allowed to move much more freely in that liquid. That is going from order to disorder. Okay? Okay. Now, the way we write this
Cool.
mathematically, the shift from a...
Wait a minute. What just happened? Was there a cut there? Let's go back. Watch that again.
Okay? Okay.
There was a cut there. So there's some post-processing happening here. So I think it has a live audience, but he still sits down afterwards and does some cuts. And well, I'll have to keep an eye out for that, because I'm always fascinated, like, what motivates somebody to go and do the editing. As you can tell watching these videos, I don't do any sticking editing. So I'm always curious to find out what happens. Now, sometimes it has to do with like privacy, like, oh shoot, had a student's face in there, right? Like, oh, I can't show that. So sometimes you have to, or basically you just can't post the video. Obviously, I'm watching this on a public YouTube site here, so this is out for the whole world. So I'm going to keep an eye out for that.
Now, the way we write this mathematically, the shift of order to disorder, is with a delta S. Delta being a change in, a final minus initial, and this S standing for entropy. Yes, I understand the idea that entropy begins with the letter E, and I just wrote the letter S, but here we are. Just another weird thing in the world of physics.
Love that.
So this delta S is a change in entropy. It's a change in order and a change in disorder. And it is equal
Did he
to
just zoom?
Q divided by the average temperature. Q, we know that is some heat. That's what we've been using when we did calorimetry, when we've talked about heat flow. That's Q. But specifically talking about this, we really care about Q being the heat added by a reversible process.
I'm thinking here whether I like that or not. I think I do, but normally we would say Q over T, delta Q over T. Like if something is held at a constant temperature, like a gigantic water bath, and you add some heat to it, it's very simple. It'd be Q over T, no problem. If you were to add some heat to something that would constantly change its temperature, you sort of have to do it in tiny little baby steps, a little dq over the current T, and you'd have to integrate that. So there's no question that Q over T average is going to be close. How wrong is it? I don't think it's that wrong. I'll have to put some thought into that. But you know, my guess is this is a class that's not going to do integrals. I'm looking at his other notes in here. It's not 100% clear to me if there's if there's any integrals in this class, and so I love this. Q over T average is absolutely close, right? If you imagine doing an integral, the area under a curve, and you do the actual curve versus you do the average, right? It's pretty close. Certainly has the right units. It certainly gives you a sense of things. It'll certainly tell you if it's like the sign of it. Sometimes all we care about is the sign. And I'm trying to think of a crazy example where the integral version would give you a different sign than just doing this. And if there was some crazy thing, frankly, you could just break it up into the smaller pieces, because it probably involves really interesting combinations of things. So I like that. Now, it could be that he's actually setting us up for an integral. I don't actually know, but I just wanted to pause and think about that.
Now, some processes aren't exactly reversible in the real world, but we're going to stick to reversible processes, things that are theoretically able to kind of exist. Now that everything...
Was that another cut or not? Maybe he just has a super easy key on his keyboard to turn things yellow. I'm just going to go back and watch very carefully.
Able to kind of exist.
That was definitely a cut. Watch his head.
Things that are theoretically able to kind of exist.
Now
so that everything turned yellow.
Definitely some editing.
T is just going to be one value. It's going to be an average temperature, and it's going to be in Kelvin. Proper SI units.
Have to, because otherwise you divide by 0.
When we talk about reversible, sometimes that can get confusing for thinking about. What we really mean for reversible here is that we're going to find Q, some amount of heat energy, for 2 states. Okay? And everything that we're going to talk about will be reversible. Now, in a later video, we'll actually...
It's so interesting to think about the focus on reversible processes when doing this, right? And we know why. It's because those are the calculatable ones, right? There's the rare irreversible process that has something that you can do, like free expansion of gas is a great example. But it's tough, right? Because he did spend so much time trying to motivate entropy as this measure of chaos, and it's why things flow from hot to cold. Well, things flowing from hot to cold is an irreversible process unless you throw some work at it, right? I wonder how students respond to that. Like, okay, you just told me it's this really, really cool thing, but now it's kind of like back, last semester when we were doing always frictionless pulleys and massless pulleys and frictionless blah, 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 right? And this is another example of that. We sort of sit in this safe zone of calculatable things to develop intuition so that then we can attack the tougher ones. And just looking here, he's going to be doing engine cycles, although if you do the Carnot cycle, that'll be reversible. It's not 100% clear to me that they're going to get to do something that's 100% irreversible here. Well, anyways, it's really interesting.
Actually dive into an example of what's going on here, but one of the interesting things about this idea of a change in entropy is that, in general, the change of entropy is equal to the change in entropy of a system plus the change of entropy in the environment. And this always has to be greater than or equal to 0 for any real process. For any real process, this must be true.
I heard a really, really interesting story from... I'm blanking on his name. Basically, the person who's credited for inventing the laser. So it was at, I think it was an APS meeting, maybe in 1996 or something. And it was fascinating because he was talking about back in the 40s and 50s when people were talking about the potential of a laser, or even at the time a maser, right? They're like, okay, well, it kind of seems like we might be able to do this. We could really extract some energy out of this in a coherent way. But a few people would sort of write down on a napkin and say, wait a minute. To do that, you need an inverted energy system. You need more particles in the higher energy state than the lower energy state. And these sort of entropy arguments made them think, I don't think that's possible, so never mind. And apparently, this is the way he told the story, so who knows, but he was saying how they thought, well, hang on a second, if we define the system large enough, we can have a really crazy situation of some particles, some electrons in the higher energy state than they are in the lower state, as long as the larger system sort of takes care of the rest of the entropy. And again, the way he told the story, like a month later, they had it working, right? Like it was just like this psychological barrier for them because of things like this, right? So the universe is not going to let us do this, but it was really carefully understanding this left-hand side to say, wait a minute, this can be crazy and weird, and we just might have to make up for it here. Lasers are not overly efficient. Lasers require a lot of sort of other infrastructure around them to get it to work. But to me, that psychological barrier to hear that story was fascinating.
If we knock a plate off of a table, that plate's going to shatter into a bunch of pieces. That makes sense.
Witness.
We've never seen a scenario where a bunch of pieces of plate on the floor have reconfigured themselves and then put themselves back onto the table. That's not a thing.
Also witness.
If it was a thing, please let me know. You've discovered magic. I need to know about this because we can exploit it for our own nefarious gains. In general,
That's
the
awesome.
entropy of the universe, and that is what this delta S is right here, must always increase.
Or stay the
It
same.
must always increase for any
Or stay
real
the same.
process. Even if your change in entropy in a specific system is going down, things are becoming more ordered, such as in like a refrigerator. On a global scale, that refrigerator is still pulling power from somewhere, and that power needs to be generated. So on the environmental side of things, we are still generating more entropy. The universe entropy is increasing. Okay? It always must be greater than or equal to 0. To have 0 entropy, nothing is allowed to happen. But I guess technically, nothing could happen. In which case, if everything paused for a second, our entropy wouldn't change. So with this in mind, where does this leave us? Well, it leaves us with a few weird things to talk about. The first being, when we look into engines, because that's what we've been talking about in this class, kind of like heat engines and refrigeration cycles. When we look at engines, we have to have a change in temperature to do work. That was one of the features. We had to have some hot reservoir, and we had to have some cool reservoir, and we went from hot to cold, and then we snaked out a little bit for work. That was one of the efficiency diagrams we looked at.
Love it.
We have to have a change in temperature to do work. Something that can happen, though, is as this entropy increases, as we heat up cold things to warmer positions or more disorderly systems, more chaos, the temperatures are getting closer. Given a long enough time, all of the molecules in existence will interact with all of the molecules in existence, which means that everything will be the same temperature. And if everything is the same temperature, you can no longer do useful work. You will just have stuff, and you can't do anything with it. This is what we refer to as the inevitable heat death of the universe. Just
I like that.
over.
I like the way he really couched that. That was really great.
Anymore. Not even like you, but atoms in general can't do anything because they're just all the same temperature. So nothing useful can become of that. The universe will literally just, die. It'll just stop doing anything.
Depressing.
So that's an inevitable heat death due to this idea of entropy. Another idea that we get.
It's interesting, right? So there's the Great Crunch theories that have been around for a few decades about how the universe could end. So I think if you do the Great Crunch, which basically says that, I don't know, I was going to say that gravity eventually wins, right? Like that the Big Bang flings stuff out, but eventually gravity sucks it back down again. I actually think if that were to happen, we wouldn't have this problem that he's talking about. But of course, we no longer think that's true because all this weirdo dark energy just keeps saying, keep going, guys, keep on going, don't come back now. And so we usually think about the loneliness of the end of the universe, but he's also talking about the homogeneity, right? If everybody's the same temperature is bleh, right? There's nothing interesting that can happen any longer. I think that's really interesting.
From entropy is since this delta S of the universe always has to be greater than or equal to 0, and we said that it can only equal 0 if we've like stopped time for a second and nothing happens. This implies that since this delta S of the universe will be some positive value as long as time is ticking, this implies that this entropy is the arrow of time. It's time's arrow.
Cool.
It implies that time can only go in one direction.
That was awesome.
Because for time to go backwards, you would have to reorder systems. And we cannot reorder systems. Systems must always go to disorder.
Very cool.
On a universal scale. So because of this, you can't time travel. You cannot go back and relive your 6th birthday. It's not possible. And any movie that says you can, well, they're wrong.
All right, I'm going to pause right there. Some really, really great stuff at the end. I think that lots of really interesting things in here. I think that it's a super, super tough thing. Doing it from the microscopic perspective where you're counting states is how some books approach this, but that's super tough because mathematically it takes a while to get there. This idea that, well, it depends how much temperature you have and how much heat I give you, he'll eventually get to that with how his fraction works. But this stuff here at the end I thought was just really, really great because you have to spend this time thinking about why are we studying this in the first place. So really, really cool. All right, everybody. Well, have a great day. And remember, physics teachers are awesome.